Right, where A is this Cartan matrix.
And this.
And who is P and who is Q?
So let me write it down.
Mm-hmm.
So Q is the where alpha I are simple roots, and it represents an integer. So this is a this is called a root lattice, and P is all such lambda belong to our Euclidean space such that for all so we need to take the quotient of this side and try to, like it's the cardinality of this, and we need to calculate the determinant and show that these are equivalent. So the elements of Cartan matrix.
But why one is inside another? So you need Q to be inside P, right?
Inside P, yeah.
So why is that?
Because actually I don't understand this side.
Mm-hmm.
This side, but
So first of all, P. So Q is a subset of P. So let us see that. Why is that true? So what do you need to check? The person you just need to take any element from Q and check this condition that you have in the definition of P, right?
right.
So let's do this.
So I can take any integer alpha I,
Yes.
and just put it, replace it by lambda.
Okay.
So we have any okay, so like any integer, I write it like this. So an integer and
So what do you need to check?
and we need to check that this is an integer.
Okay.
This whole thing is an integer. So
Why it is an integer?
I mean, no, it's not an integer. We need to check that it is an integer.
Okay, so
any root can be written as summation of alpha i's,
yes.
where these are they belong to z. So but these are simple roots. So the formal basis, so there must be orthogonal all of them, and we will only have
Alpha i's are not orthogonal with respect to this.
these are not orthogonal.
These are not orthogonal. They form a basis, but it's not orthogonal with respect to this form. Okay, so what are defining properties of root systems?
They should span the our Euclidean space.
Yes.
And there are four properties. One second, I need to check.
So one of the properties is something is integer.
Yeah. This inner product has to be oh yes. N alpha beta has to be an integer.
Right, and what is n alpha beta?
It is just you can add it to. Right? So this is integer. Okay, so.
So therefore, what is written there is n times some integer, right?
Yeah. So it's just n times like n1 times some integer. So it just belongs to z.
Okay.
Yeah, n1 times.
Okay, so that we checked, right? So Q is now subset of P, and it makes sense now to take quotient, right? You just glue together points of P that belong to Q, right? And so now the question is, what is the size? What is the size? How many elements does this set have? Do you have any ideas how to do that?
I need to think. I think maybe.
Yeah, so if not, then not. Okay, you show that at least Q is inside P. Then we can proceed. So just it's okay to say no if you don't have any ideas.
I don't know.
Okay, so then
this side.
okay.
I tried some things, but maybe.
Okay, so what you would like to?
Actually did some calculations, but yeah, I'm
All
not
right,
sure.
all right.
Also, my idea has some gaps.
Mm-hmm.
First, I don't know why this guy must be positive, and also I changed this condition, and I don't know why they are equivalent.
Why you can change here for pi?
Just because you see in there.
No, but every root is some linear combination of something from pi.
Yeah, but there is a question. We don't have any trouble here, but there is some trouble here. So
Why?
Yeah, because when we consider if here is maybe consider maybe these two guys are simple root and there is a reflection, not a reflection, just Maybe some lambda. So of course, if lambda with alpha 1 with alpha 2 with this formula is no, I'm just so I don't know why it must be integer if lambda with all simple roots is integer.
Well, all simple roots roots are obtained from simple roots by reflections. Yes, and reflections actually do not change lengths, right? So so you have something like right. So suppose that your lambda with all simple roots, right? So you would like to check that this is integer, right? If you know that lambda with if I replace alpha I with any simple roots, then this is integer. Now I would like to check this for any root. So I know that alpha is W of alpha I for some simple root. So let's see if we can. So it's 2 lambda W alpha I, right? With no, and I can replace it with this.
Okay, now I understand. Okay.
Right? Except, so maybe not so fast, because now I have to, well, I know that W inverse of lambda, right, is inside. W inverse of lambda is inside.
The inverse is also an element in the Weyl group, so this is also some S of I1 and 2 of B, and is some integer coefficient alpha 1.
Right. Right. So
So we get it.
yeah, we get it. Right. So we just prove, right, that W inverse of lambda with any alpha, right, 2 of this over alpha for any positive is integer, but then you can WX transitively on roots, right, and it actually acts on roots. So I can take W inverse alpha, right, and do the same, and then lambda with alpha also, like this is with any alpha but without this W inverse also will be integer, right? So we actually, it's not that obvious, but we can do this.
Okay.
Yes.
And how we know this is a positive number?
Why? Because it is actually a gram matrix of alphas times diagonal matrix with so it is d1 dn times gram matrix of alpha 1, alpha r. So Gram matrix is this matrix with elements alpha I, alpha j, right? So determinant of this is positive, of Gram matrix is positive, because of because it defines like an inner product for us. And these di's, they are actually, I think 1 over, or I think 2 over alpha I, alpha I. Also positive. Yes.
Okay. So I can start to.
Yes. So these two things we accept. Mm-hmm.
We can first pour some pictures to mix everything here.
Mm-hmm.
So maybe we can just consider this case, and these two guys are the simple roots of some root system. So this guy is the lattice of generated by these two vectors.
Mm-hmm.
And
So when you say lattice generated by these two vectors, you mean exactly what's written here, right? Yeah, so if I have a lattice with a basis consisting of vectors v1, vk, right, then L, this lattice, is direct sum of z times vi as I runs from 1 to k. So this is by definition what it means to have a lattice with such a basis, right? That's why it's called root lattice. So the question is why this is called lattice.
why this is a lattice is because for any and this is also lattice is because for any two elements from here, maybe lambda 1, lambda 2, and the sum of lambda 1, lambda 2 is also satisfying this condition.
Yeah, but also you can have basis there.
Basis.
Yeah, so basis it's also important for representation theory that we'll start next time. But the basis here is the dual with respect to this. So omega I is defined as follows: is that omega I with alpha j over 2 alpha j is delta ij. So I can define vectors omega 1, omega 2, and so on, omega r, by these relations. So these are called fundamental weights. And then all elements in P are then sum over z omega i's. I from 1 to r. So in this picture, so you had third vector here, right? And your omega 1 is this one. Omega 2 is this one, and omega 1 is this one. So omega 1 projects to alpha 2 as 0, and it projects to alpha 1 like to the middle of alpha 1. That's exactly why we have 2 here. And the same here. So it is orthogonal to alpha 1 and projects to alpha 2 to the middle. And so root lattice is this thing. And then you just need to draw all the parallelepipeds, right? And find all these vertices. So this is root lattice. And weight lattice in this case is this. And then this as well. And more. So I need also middles of triangles. So I have more green arrows and some of green vertices, and some of green vertices also red vertices. So red vertices is a subset of green vertices, which is root lattice. So that's how it looks like. I have one here, one here, here, and as well.
So actually, I don't use this thing.
If you would like to, you can use this, or you can not use.
I just formulate something.
So why weight lattice is this one? You can just check that any element from here belongs to here. On the other hand, you can just decompose. So suppose you have lambda like that, right? And you can just then okay, we can just take some lambda from P, right? We can write lambda as some. So this is also a basis. It's just some different bases. We have basis alpha 1, alpha r, and basis omega 1, omega r, right? So I can write down some decomposition in this basis of lambda, right? But then I can take lambda with alpha i's. If I, like this. This is exactly AI. But because lambda I took from there, AI's should be integers. So if I take lambda from there, it decomposes in omegas with integer coefficients. So therefore, it's inside this lattice. So we have two-way inclusion. Yes. Mm-hmm. Okay, so how to proceed then?
So my way is that to reformulate this set and find some connection with this matrix. So we just consider that because these guys alpha I, alpha 1, alpha 2, alpha r, they are simple roots, so they are basis of our Euclidean space. So any element here that's denoted by x, we can write it in some formula xi. Yeah, and we try to solve this equation, which satisfies this condition. This equation, how to solve it? Just take this formula to here, and we got 2x alpha. Because we have already changed it to the
Yes, okay.
Just for any g, 1 to r. Here should be g. So this should be an
Integer.
And then to use this formula, we got xi times, if we change this to alpha I, then we get
Ji.
Yes. And this is, and we need OG, that this sum should be some integer.
Mm-hmm.
So it means if we write it to the matrix formula, we got
Mm-hmm.
this times this matrix times the sum.
Mm-hmm.
Vector, it's belongs to ZR.
Mm-hmm.
Yeah, and we need a quotient here. So we must restrict everything in this box.
Yes.
So what does it mean? It means all the xi, it should specify this condition.
Yes.
Yeah. And now we just rewrite this thing to be
Mm-hmm.
this set should be
X in
x in R.
mm-hmm.
Such that Ex should be an integer.
Mm-hmm.
R. Yes. Okay, and we can. It should be R.
Mm-hmm.
Next is. Just rewrite this thing to be x.
Mm-hmm.
Wait a minute, this so here is so it is actually the image of if we consider E as a map from
Mm-hmm.
E to E. So this set is actually the image of this area,
Mm-hmm.
and we count the. So we have some 0, 1, 1, this image after the mapping. We get something like this, and we count the lattice. We count the vertex. It contains in
Yes.
this
Mhm.
part, and
Mhm.
and we know the green points are also from lattice.
Mm-hmm.
We know some theorem from geometry
Mm-hmm.
that the area of the image of this part is the number of this point.
Area in what unit, though?
Area of what unit? Unit is this.
Yes.
When we choose it be the length 1.
Yes.
Yeah.
Or in other words, you just distort. You take this this domain, right, and make a deformation of this such that this becomes a unit square. So well, these are sides of unit square. Then then you would like to compute. So unit square is the unit of the area that you would like to have, right? And you are computing the area of this thing in this units of area.
is the determinant of the maybe add some absolute value. That's why I must prove
Yes.
this guy is positive network.
Yes. Yes.
This is my proof.
No, still something. Yes. Yes.
Still something. I need to
Still
mention
something
that,
to. Yeah.
Why we have in order to use this geometry theory, we must check that all the points in all these points are also in the lattice, and actually we have done it. Person done it.
Okay. Well, what O was saying is that you check that Q is inside P, right?
Yeah. Q
Okay.
is at P, and this how is it? Vertices in the point in the vertex is included in our lattice. Then we have this area of this is equal to the number of points.
Okay. Okay.
Maybe the theorem I use is called I forget the name. Maybe the name is this.
There's one also. Okay. Any comments, questions? Should we repeat something? What's going on here? So the point is that if I so how I understand what's going on here is the following. So let's look at the picture here for A2, right? This P quotient by Q means that we have to compute how many green points is inside this domain, but we should be careful about the boundary. For example, this point we should count, this we don't want to count, right? Right. So in this case, how many? So for A2, we would like to count this one, so 3, right? And this one is already an image of this one, right? So actually, we have 3, right? And now let us count how many. So now let me consider the parallelepiped which is spanned by these two vectors. This one. Maybe let me use the green since I'm ready. So this one. So let me find how many, how this area of this bigger parallelepiped spanned by alpha, in how many times it's bigger than the area of this parallelepiped. Should be 3 times bigger, right? Because I also have yes. So I also have this one. I also have this one. Also have this one and this one. So let me compute areas. So one, which are inside. So inside this, right? So one here, and then another one is given from these two halves, right? So 1, 2, and 3. So you just, since we take a quotient, you just need to connect these two lines and these two lines. All right? And I have 3 fundamental domains of smaller lattice inside the bigger lattice. Okay? Is that clear what I'm hand waving here? So the domains that are bounded by these green edges are small ones, and domain which is bounded by white edge is a big one. Okay, so I am trying to compute how many area-wise domains, green domains inside the white one. Okay, there's one inside which is whole thing. Then we have two halves, one half and another half, which makes me another one. And these are two halves, which gives me another one. So I have three inside the white one, right? So the area of the green one is 3 times smaller than the area of the white one. And that's exactly the number of points that I have to compute inside this smaller domain. Okay, and so this argument that I'm making is that right, I need to compute area of something that is spanned of how should I say it? The parallelepiped with edges alpha 1 and so on alpha r. But again, area in which units? So unit of area here is the parallelepiped which is spanned by omegas that I introduced. Right? So let me again write this down. Here are omegas, but I erased them. So where unit of area is parallelepiped with edges omega 1, omega r, where omegas are those so omega I alpha j over alpha j is delta ij. So this is definition of omegas. But then we know how to compute. So if I have a bunch of vectors and I know their coordinates in say standard vectors, if I decompose in standard vectors, then I know from geometry that area of the parallelepiped that is spanned with edges of these vectors that I started is exactly the determinant of a matrix given by these coordinates. Okay, so let me again. So if I have V1, V2, again Vk, and Vi is say Nij, Ej, sum over J. Let me consider matrix N. Then I claim that, here I shouldn't say area, I should say rather volume, right? It's like R's dimensional volume, right? Volume of then parallelepiped with edges V1, Vk is what? Is exactly determinant of this matrix N. So this is some elementary geometry. There are different ways how to prove that. But okay, this is believable. That's what people learn like in some first years of the universities, or I don't know. But then let me now take alpha. So I should take alpha and decompose it in omegas, right? And then take the determinant of this matrix. And this gives me exactly the size of this set then. But what are these nij's? I can compute it. I can take alpha. Sorry, alpha I here, right? This I corresponds to the simple root. So my parallelepiped is spanned by simple roots. So I take alpha I and compute inner product, not inner product, but rather this. And plug this inside. Then I will have exactly nij, like, well, I will have sum over j, right? But omega j with omega I with any, okay, let me plug this inside. I will have sum over nij, and then I will have 2 omega I alpha j over alpha j alpha j. But this is delta ij, right? Just from the definition of omegas. So therefore, this is just, so ij here. Maybe index of summation should be some not j from here, but j prime maybe. Sum over j prime. But this is exactly nij. Sorry, omega should be here. So I plug in what? This. So omega I. Something is bad with indexes, right? Yes, I should say maybe not j here, not j prime here, but rather I prime. Yes. Yes, I prime. In any case, it should be nij. Right? And so therefore, these numbers, these are exactly, and this is exactly aij. These are exactly maybe ji. So what stays here is exactly the elements of Cartan matrix. And so therefore, to compute the volume or the size of this set, I need to take determinant of Cartan matrix. Okay, so enough of that. Let's go. Okay, Christina, you wanted number 2. She found some solution, but there might be some problem with the solution. So our task is to find what's wrong.
Yeah, and put this
Okay.
to that guy who sent it.
Yeah. Okay.
Yeah, that was the sketch, and I tried to complete it, and I completed that, but I'm not sure that some steps is correct.
Mm-hmm.
It was about that. Okay, firstly, I will repeat definition. If R is reducible, we can imagine R as 2 smaller subsets.
Mm-hmm.
And otherwise, R is irreducible, and we wanted to prove that if irreducible,
Mm-hmm.
I will put like this. irreducible, so it means that it's not a root system. It's not a root. Yeah. And first thing that I need to mention is
I think opposite.
point.
It is a root, yes.
Sorry. Yeah, that's a contradiction. That's a
Mhm, mhm.
zero. Yeah. Okay, and first thing that we need to mention that we will use that fact that the Weyl group act on a Weyl group generated by
Mhm. Simple reflections.
how that's called, reflections
Yes.
as alpha I.
Mhm.
And it act transitively on set of root system.
Mhm.
So, like, I mean, transitively, that's our group has only one orbit.
Mhm.
So it will mean that for example, we can take, okay, maybe not like this. Yeah.
You use that's not completely true. So you're saying that root that Weyl group acts transitively.
Yeah, on set of root system. It's not true.
No, I think it's not true because, for example, we have roots of different sizes, of different lengths,
Okay.
and maybe we don't need even that. So why do we need?
No.
So technically, what you're saying is not true because you can have, like, in B2 you have two different lengths. And if you act by Weyl group, it will never give you different length because you just reflect, right? If you take one,
This reduced root system, so everything is.
no. So for example, in B2, in A2 it's correct what you're saying. So in B2 you have this, right? It is reduced, right? So try getting this root out of this by action of Weyl group. So you will never do this because this one is longer. And if you reflect, you get the same length. But maybe you don't need this. Let us all agree that this statement is only. So actually the statement is the following: that a Weyl group acts on roots, transitively on roots of the same size.
That one is reducible or is irreducible?
This one is reduced, irreducible.
It's irreducible?
Yes.
It is irreducible.
But
Okay.
if it's irreducible, then these the
The
bases that
orthogonal
are
set?
of different sizes, they act only.
No, they are not orthogonal. It's all in the same plane.
Yes.
Okay.
But why is it
So this is an example, of reducible. So you have R1 is this, R2 is this. They are orthogonal. This cannot be decomposed into two sets which are orthogonal. So how? If you think opposite, you can try to decompose this into two orthogonal sets. How?
But we cannot take like this part. It cannot be like this, and this will be orthogonal to this, no?
But they are not orthogonal. This is not orthogonal to this one. Everything in first R1 should be orthogonal to everything in the second R. Yes, so.
Okay, now it's more difficult because I wanted to use fact that's we all the time for any
But why do we need it? Maybe you don't need it in this thing. Okay.
Oh, I think okay, I will say that
Uh-huh.
Okay, if it's transitive, we can say that exist alpha and beta roots, and such that we can find all the time element of W. That's it will look like beta equals to B of alpha. But if it's not transitive,
This is not true.
no, we anyway can find.
Yeah, if you fix for any pair of roots, this is not true. But if you just need, if you fix beta, then you can find alpha, of course. Such that this is true.
Okay.
But you continue. Maybe you don't even know this. You don't need this for any pair.
Okay, yeah. If
So
we
just
fix
continue.
one of this and
Let's try to
find
fix this.
other, yeah, okay. So maybe you can use this fact. Okay, next step it was to like define function that's okay. No. Firstly, we will assume that our alpha 1 plus alpha 2 plus alpha r is not a root.
To prove by contradiction,
Yeah.
right?
And then we want to say that exists a function f such that if this is not root, our function no, okay, works in E. Alpha 1 plus alpha.
You mean element of E star,
Zero.
right? So function
Like-
linear map from
Yeah.
E to C.
Yeah, and this strange argument, like they say, like, okay, so let's exist function that if it's not root, it will be zero. But if it's root, as I can guess, if it's root, so f of, for example, we have for roots alpha I, yeah. So all they will be not zero. So they say, like, okay, let's exist this function. Can it exist? May it exist?
It may, I think it may exist even without assumption that this is not the root. So if you take any vector, there is this non-zero, of course, functional that such that if you plug in this vector in this functional, it's not zero. So far it's okay, but it's, you don't not need the assumption that it's not root yet. Okay.
Yeah, but and another step is we will take. They consider root, as they say, root. That's look because alpha 1 is root. So now it will be tricky. Like, okay, this is root, and they say, like, let's consider root. That will look like alpha 2 plus. So they took out only alpha 1 and say that this is root. But I offer to use by induction, like to take. Okay, maybe I can show this step, and then I will change it to how I did it. I think.
So, did you claim beta is a root?
Yeah, and I think that this not true because why is it true?
Yeah.
Yeah, that's.
Maybe it's true, but you need.
Yeah, so
No,
like
I
I
don't-
will finish because it's only one step. The rest. Yeah, but then I will change this fact to more true fact. Okay, so and now, okay, let's consider function f of our beta. So it will be f of no. 1 second. No. I forgot here. I still can understand why it can be root because, like, to get that's beta will be root, we need that this will be root, yeah? But,
You suppose this is not root? Oh, 2.
yeah, it's 2. Okay, they say that let's consider this root. And then I will change it later because I also don't really like how it's. And then we can use our reflection, and we can rewrite this because it's this element. It's a product of our reflection. Yes. So
It's a product of reflections. Yes.
so we can rewrite it like
Simple reflections. Mhm.
like this. If I write it this correctly.
But why the first one is alpha 1? It's a product of some reflections.
Yeah. One second, maybe they mean.
Well, of course you can always multiply what you have. Yeah, I mean, sure.
Excuse me.
You, huh?
I tried something and I wanted to discuss something the same problem and
Okay, maybe after we figure out what's wrong here. So yeah, sure, you can do something like this, but maybe not. I don't know. So W is what? Is something. You don't know even what it is.
Yeah,
You of course can take S alpha 1, S alpha 1 W. So, but then you claim that this is.
like alpha 1 is root. Yeah, so we can all the time like send from one root alpha 1 by this element to another alpha. Like I think for can I say that for any alpha I can find element v such that like any alpha like alpha 1 alpha. So
This is also not. So for any alpha there exists W.
yeah, but this is
Not for alpha 1. And there exists W and there exists alpha I, such that this is true. So this alpha, it's not true that everything can be
but yeah, for that
made
I
out
asked
of alpha
for
1.
transitivity. I thought
Yeah.
that can help.
Well, we don't have transitivity,
Yeah,
but
okay, that's a problem.
yeah.
I think maybe it was that notation.
But still not clear why you can take, like why you replace this by this.
But if you replace that W with that, one that you put in the right.
Sure, but then okay, then whatever. But it's not SW alpha 1, right? So this one is not SW alpha 1.
No, it will be.
This is just some other element of, right? Sure, but then what?
Then like I think I saw this like some property from element of Weyl group that we can rewrite all the time like this.
Mm-hmm.
But I'm not sure about maybe I confused something.
No, so not clear how to go from here to here. Not clear why this is
Yeah,
true.
but this I will. I think maybe correct.
Yeah, okay. I think we accumulated too many not clear things.
But this okay. This I wanted to fix it by induction, like just to consider root instead of 1.
Mm-hmm.
And okay, that's this is another property that's this is oh no all this like we can rewrite like f of alpha 2 and then because we say that this is a root, so it cannot be 0. but as as they did, because I still.
Why this is not 0?
Because we say that our function works like it's 0 if it's not root, and it's not 0 if it's root. So if we say that this is root, it cannot be 0.
Ah, so that's not what you need from the function. Not this condition. Your defining condition for a function is that it should be 0
Yeah,
if it's
not root.
root.
Yeah, so the function works like it's 0 if it's not root, and it's not 0 if it's root. And then we wanted, but
Yes.
like I also didn't like this, so I offer to use by induction, like doing this, and consider the same, but instead of beta, instead of this, it will be alpha 1. No. But, no. I want to consider not by induction, yeah, but like this. Okay, so. Second. If it's not 0, but we can consider if because function is linear. We can consider this. It will be f of alpha 1. Yeah. But okay, for our first thing, we say that this is 0, and this is not 0, and I know. Because I got this idea during OC speech, so I'm not sure how I wanted to do.
Okay, so maybe Sanchita can share some thoughts. I honestly don't understand this.
Okay,
so
if I can fix that, but I cannot. As I thought that it was some property that I also found in Wikipedia, something like this. Maybe
okay.
I even rewrite.
It's okay to find something in Wikipedia if you can prove it using our something that we prove in lectures. So that should be okay.
I also have some holes,
Uh-huh.
but maybe we can discuss that.
Uh-huh.
So, okay, what we have is that it's just alpha 1 up to say alpha r, and it's of course an irreducible system. Okay, and we have, and they are all simple roots, so we have this property j is less than or equal to 0 for simple roots. Okay, and let's say alpha 1 is of course simple root. I can also prove the same for, also today only we discussed this, that if this is the case, then alpha I plus alpha j is
a root, yes.
Okay. So I can say that by induction, I can take, let's say, alpha 1, comma, let's say alpha 2 by definition. So alpha 1 plus alpha 2 is a root, and I can go up, and then up to, let's say, plus alpha r.
So this is not, it's not true. So here you have
Yes.
not strict inequality,
Yes,
right?
yes, that's what I was a bit confused. Like, I know if I can prove this part, then I can use induction and then claim, this is my simple root.
Yes, yes.
And okay, this
Actually, it's not true.
what is not true?
If it's 0.
Yeah, but we are trying to
It's an
fix this.
orthogonal.
We are trying to
That's what
fix
I was
this.
thinking.
Yes.
Okay, so okay, this is the thing that I need to think, and that's what I was asking. That if we have this, then they belong to equal to 0. Let's say, so they belong to like an orthogonal system, or
Yes.
we
Yes.
cannot have this kind of situation. So that was my kind of justification why we cannot have a.
Yeah, you just need to apply some statement which is clear,
Yes.
right, to this.
Yes, so that's what I was thinking.
Right. So let's do this. That's a correct way to do this. You just need to pull this to no, to clear way, to clear proof, right? So you almost did everything. You just it's not like it's just not necessary to go 1, 2, 3, and so you can take first to be alpha 1, right? And then you say, okay, I will need just at least one root out of rest alpha 2 so on alpha r, such that alpha 1 with this alpha j is strictly less than 0. If I don't have 1, then alpha 1 is orthogonal to the rest of them. But it cannot happen because our root system is irreducible.
Yes.
Right? So at least one we can find such that, say, I2, right? Such that it is like that. But this means that alpha 1 plus alpha I2 is a root. But then you proceed, you say, okay, so now let me consider the rest of roots that I never used here. Okay, so then I need to find next root, alpha I3, such that its inner product with alpha 1 is strictly less than 0. And so at least with one of these two is strictly less than 0. Right? So we need alpha I3, so we need existence of alpha I3 such that alpha 1 with alpha I3 is less than 0. Or alpha I2 with alpha I3 is less than 0. If such root doesn't exist, it means that it is orthogonal. So then all the rest is orthogonal to both of this. And again, we have our system reducible. So therefore, this root exists, and therefore its inner product with alpha 1 plus alpha I2 is less than 0. So therefore, alpha 1 plus alpha I2 plus alpha I3 is a root. But then you just continue. You take the fourth one. It should be less than 0 with at least one of these two. If I cannot find one, then again, my system is reducible. And so therefore, you just, by these subsequent steps, you just get to the end. And at the end, you will have sum of all alpha i's. Yeah. Okay, so we are out of time, but we started a bit late. Maybe we can do one more problem. Okay, 8.3 was, or maybe somebody wants to do some problem on the desk, on the board. Do we have suggestions? No?
I want to be
Okay, so which problem do you want to?
Three.
Okay, 3? Yeah, okay.
And for problem 3, we should first know some facts.
Mm-hmm.
For two simples, if they are orthogonal and if they are orthogonal,
Mm-hmm.
and alpha 1 plus alpha 2 is not a root.
Okay.
It's the two-dimensional. You can check.
You can check, yes. That is only for simple roots.
Yes, for
Mhm.
simple. And we want to prove that. Then I want to prove one thing is that for let's see. It cannot be something like this. We can choose some some orthogonal alpha 1, alpha 2, and then this is simultaneously irreducible. I will prove this cannot happen.
Can you say it more clear? So what is R1 and R2?
Just I mean the collection of the a group of simple roots.
Okay.
No, not the simple roots, just the roots.
Okay. So how it's related to what you wrote above? How is it related to the formula that is above this? R1 and R2.
I haven't used this. I didn't talk about the formula yet.
Yes.
I just want to prove that how to form it. We cannot find some orthogonal sets of roots such that it's irreducible in R1 in R1 is irreducible and R2 is irreducible.
And their union is whole thing?
Yeah.
But this is just by definition. And they are orthogonal?
Yes.
So this is just by definition of irreducible root system, you cannot
Yes,
find
yes.
them.
Yes, yes.
So nothing to prove yet.
Yes.
Okay.
And
So you, by condition of problems, your root system is irreducible. So therefore you cannot find such R1 and R2.
this is the second thing I will use.
Uh-huh.
And the third thing I will use is that in any abstract root system we have only two kind of length. At the most two kind of length. It's not the same.
Say it again, sorry. So.
For a root system,
Uh-huh.
and we can at most find two kind of lengths. Just
Yes,
the long
that's
one and the short one.
That's for rank 2 it's clear.
Yeah.
For any rank it's not clear, but it follows from classification, right?
Yes.
Okay. So you're using what we covered today on the lecture. Sure.
Okay.
Why not?
And I think that's almost prove these things.
Mm-hmm.
First we choose. And suppose it can be written. I mean the support can be written as a disjoint union of two non.
Mm-hmm. Mm-hmm. Okay.
And you consider the simple roots since the elements here are some simple roots.
Yes.
And so element into these two are the simple roots.
Yes.
And you can consider the simple roots here.
Mm-hmm.
If this happened, what does it mean? It means in the subspace. What the subspace I just means? For example,
You just consider span of support of alpha, right?
yes, that's what
Yes.
I mean. You consider this. If there are three simple roots, you consider these three subspace. You can in your root system you can have more, but we just consider this in the simple roots. And this happens if alpha 1 is here, alpha 2, alpha 3 is here, and these will be irreducible root system. Two orthogonal irreducible set here. But we just prove this cannot.
But sorry, this cannot be for. So I'm sorry. So you're taking. Oops. So you're taking. What you're saying is that I have E, right, and root system is root system of Euclidean space. Then I have U1 and U2, right? I have support of alpha. And it is some subset of R. And then you're saying, let's consider E prime, which is span of support of alpha.
Yes.
So you consider some subspace, right? But then E prime intersect R will be some root subspace. Will be some root system in E prime. So this is root system of E prime, right? And support of alpha is exactly simple roots of R prime, right? It's a simple, so it's pi prime, simple roots of R prime. Why is that? Something careful should be said, right? So suppose, yes.
Orthogonal, they are orthogonal? I mean,
Yes. So what we are trying to do is that is to have So U1 and U2 they are orthogonal. Yes, we're going to use that in a minute, right? But I'm just kind of saying clearly what Zonghao actually said. So suppose we have support, and now I would like to restrict myself to a subspace of E spanned by this support, right? Then I try to intersect this my root system with this subspace. This will be some smaller root system of the which of rank of this of dimension of this subspace. Okay, this some root system smaller in this smaller subspace. Okay, and moreover, support of alpha, it was simple roots of R, but of course they should remain simple for R prime as well, because if I found two elements of R prime such like positive, right? They are also positive roots of R, and if their sum is in pi prime, then of course the same happens in R, right? So in the beginning, then we had not a simple root, so there's some contradiction, right? So pi prime is also simple roots, and of course these are all simple roots, because we chose our subspace of the same dimension as pi prime. So we cannot have more simple roots for R prime, because otherwise we would not have a basis, right? Yes, and so then what?
I will use these two. There are two kind of lengths.
Okay.
And yes, if this happens and this is irreducible, and we can know alpha, this are a root, right?
Mm-hmm.
And this is also a root. And if the length of these two are different.
Why this is I don't know. So what's going on? You just so your support. Suppose you have support like this. U1 is orthogonal to U2.
Yes.
Right. Then what you're saying?
And
You just take
two
A.
are irreducible.
Nah.
The irreducible subspace.
They are irreducible in what sense? They are not okay. Irreducible in the sense of root systems, right? So they are not a disjoint union of orthogonal
And by
systems.
the previous problem, if it is irreducible, these are two simple roots, and this is a root,
Okay.
and this is a root.
So you take all simple roots here,
Yes.
consider their sum.
Yeah.
Take all simple roots here, consider their sum. And they, since you assume that U1 and U2 are irreducible, of course, these two sums are roots. Yes.
And if the length if the length of these two are different,
Mm-hmm.
then we will by the Pythagorean theorem that we will produce a third length.
Of the third length, you mean?
Yes.
Okay. So you're saying if I take two orthogonal vectors of different lengths and consider their sum,
Yes.
then the sum will be of length of third length. Yes, I think that's true. Okay. This is just because of triangle inequality, right?
Yes.
L1 plus L2. No. So I'm sorry, but why is that true? So if I take,
Since your system is orthogonal.
yes, if I take two orthogonal vectors, v1, v2, so v3 of length L1, L2, and v3 has length L3, well, we have, of course, a Pythagorean theorem.
Yes.
And you're saying that L3 cannot be equal to, of course, yes. L3 cannot equal to L1, L2. Yes, and then if L1 and L2 are not equal, then we have L1, L2, L3 are all different. Yes, okay, I agree.
And
Agree.
if they are equal, we reduce to these kind of situation. And this can still be a since we're in two-dimensional situation, if we have the root of the same length,
Yes.
it's kind of and
Ah.
cannot be
Yes, so first of all, they cannot be right. So if these two are equal, then we are in this situation. But maybe we don't even need this condition. So if I have alpha 1 and alpha 2, which is orthogonal, so your fact actually includes that alpha 1 should be of the same length as alpha 2, right? Maybe you don't even need this. Is it true that we can reduce this condition that they should be of the same length? Yeah, I think you can do it. You can do it without any considerations of length, right? You take two simple roots, right? Then, if they are orthogonal, then alpha 1 plus alpha 2 is not a root in a reduced system, right? But why your system is reduced, though? Yeah, so here you had this condition that U1 and U2 is irreducible.
Yes.
But what if it's not?
Decompose two.
Then I decompose 2, and so what? Then I have more than 2. It's not then reduced to this case. So your proof only works with the assumption when you have decomposition to irreducible. U1 and U2, right?
Oh.
What if they are not? It's not reducible.
If they are not irreducible, we can just consider the just decompose.
Well, if we decompose it further, you cannot reduce it to this fact. Because then you have not 2 components, but more. And then this is already doesn't work.
Can I ask
Yeah.
for it why it is correct?
Yes.
Okay.
You see that? Yes, the
I see.
problem.
I see.
Yeah. Uh-huh.
Mine also has an algebra where I just use things from
We kind of trying to use the few things from different problems.
Okay, I will
Okay, so yeah.
I just want to ask.
Uh-huh,
I don't know. Okay, so I have this alpha, is a root. So either it's r plus or r minus. So I will assume that it's positive. It's positive root. So this. All these integers are positive. Okay, and I will, how do you say? I will relabel some of these coefficients are 0, but I consider the support of alpha. I will rename the roots so that I have something like this. This is the support. And by contradiction, So you are considering that some of this n is 0? No, greater than 0.
Yeah, they might be 0, right?
But isn't that the problem in the condition given 8.3 that ni is not 0?
Yeah, this is support.
Yeah, well, here the sum is over all I from 1 to r, and here she takes smaller.
Yeah, okay. So this is the support. I rename the roots, so they are alpha 1 to alpha L. And suppose, by contradiction, that this support can be decomposed as the union of, let's say that this,
Okay.
when these two, where these two sets are
Orthogonal, okay.
totally orthogonal. So suppose this is the case, and what I do here, it's I write this linear combination alpha, and what I will do here is to write, let's say I will have n1, alpha 1, theta, and k, alpha k, and suppose these alphas are in one of these sets, in A1. These alphas from alpha 1 to alpha k are here. And then the remaining
Okay.
in the these guys are in A2.
Okay.
And so we are assuming that these are orthogonal to the ones here. So what I can do now is to consider a simple reflection of this root. So I consider, let's say, S alpha 1 of alpha. And we know that the simple reflections are permuting the positive roots. Okay, we can try to prove that. I didn't do it, but if we use this fact,
It's not completely true. The simple reflections permute all positive roots except alpha 1.
except this one.
Alpha 1 goes to negative alpha 1.
Yeah. Oh, okay.
Yes.
Doesn't matter, but if I compute this thing, we will get negative n1 alpha 1. Some I have some scalars here, and I equals 2k is alpha 1 alpha I, and then this. If I compute this reflection with respect to alpha 1, these are in the plane. These are contained in the plane that is orthogonal to alpha 1, so they are invariant under this reflection. So this guy here are the same things. So I have something like that. But this, the thing is, this is a root. So it's either in R plus or R minus. But if we look at these combinations, we have negative number here, negative coefficients, and all these guys are positive. And we cannot have this. All of them should be negative, or
all of them should be positive. I don't know, just. And maybe this is a contradiction.
This is good. Yes, I like that. What another thing that you should say that no. So this might not be. Yeah, the problem here is that these are not simple roots now. So how do you know that you will not obtain? So you need to. So this will be some roots that you have to decompose again as alpha i's, and you might obtain alpha 1 there somehow. That will again give this coefficient positive. So.
Okay, yeah, that's true.
Yeah.
Okay.
Nice try. Yes,
No.
I like that. Yes,
No, but
but
okay, I don't know. Okay. Don't know.
so actually, let me. So I understand that you fixed. I think you. So what? An easy way to do that is just continuing this. This what I wrote, right? So I actually restrict it and get a smaller root system. And moreover, this alpha is inside R prime, because it is in E prime, right? It is a really linear combination of its support, right? So and R prime is by definition the intersection of E prime and R. So alpha is inside here, so therefore it is some simple reflection. Now I use that any root can be obtained by simple reflections from simple roots, right? So it's just some SI1, SI2, and so on of some alpha ik, whatever. And this guy is inside either U1 or U2. Okay? So suppose it's inside U1 without loss of generality. Then I have simple roots here, but these simple roots are only for pi prime. So I take and reflect either with a simple root which lies in U1 or which lies in U2. So if I reflect with respect to root that lies in U1, that I'm still in U1, right? If with respect to U2, since it's orthogonal, I'm still in U1, right? So then I obtain that this is in U1. And if I started with U2, I'm still in U2. So in any case, I cannot get anything such that support is not. So in my support, what I get, it's either this empty or this is empty, right? So my alpha is actually in U1 or in U2, just because my reflections, if my other plane is orthogonal, doesn't change this plane at all. Yeah.